Hey everybody, Dr. G here with our week 3 video lecture in activity. And this one's called What the Health, right? An overview of why we should care about soil health, which is the focus of this class and really should be the focus of management across terrestrial ecosystems. We should be caring about the health of soil and how to make sure that we do the right thing time and time again. So, soil health or soil quality, we really use those interchangeably. Kind of initially, soil quality was kind of the focus in the last decade or so or more. And then more recently, we've kind of gotten more towards soil health as kind of the way that people seem to do it. Here's a basic definition: the capacity of a soil to function within ecosystem boundaries, to sustain biological productivity, maintain environmental quality, and promote plant, animal, and human health. It's really focused on what can soils give to us, but what can soils give to us while we make sure we don't screw things up, right? And there's a lot of ways to think of it, right? The soil health angle has happened more recently because people like to use human health as an analog. Soils are kind of hard to understand. They're below ground, they're brown, like what are we supposed to do with this? And so using the human health analogy has been very useful. You eat right, you exercise, you get rest, and things should go well. Eat diversity, eat vegetables, that kind of stuff, right? Some people think of it as also soil health, like, oh, a healthy soil is like a Smurf village. All these great things are happening, right? And so the truth probably lies somewhere in between. So here's my kind of stripped down version. I say that soil health is the collective effort or our consciousness to ensure that humanity persists, right? Without soil health, we're not going to have a persistent humanity, right? We're going to have problems. We're going to have famine. We're going to have lack of water quality, water quantity, things that are going to not be positive and not be beneficial, right? We've come a long way, right? Here we have the Mauna Loa plot that shows you parts per million CO2 in the atmosphere over the last 60 years, showing that we've been increasing carbon in the atmosphere. We're going to cover that again in class. We get into the carbon cycle in some detail. But issues of erosion, issues of pesticides, and other things. Ultimately, soil health comes down to how to ensure that our kids and our kids' kids will have healthy ecosystems that provide them the services that we need. Okay? So I like to think that soil health really is a critical thinking exercise, and it has 9 easy steps. Right? Here they are here. These are boiled down from a list that was provided by NRCS over a decade ago, and I've massaged them and got them into this kind of stripped down version. So, number 1, identify problems or opportunities, right? Some people see problems, others see opportunities. Determine objectives and goals. Inventory resources. That's a huge part of this. Is how do we make sure that we know what we've got, and then we can start to think up, down, management versus indicator. Analyze the results in the data. So you have an inventory, and now you can start to think, these things do this, these things do this, and you can start to put a value judgment on it. Now, provide alternatives to the ones that don't seem to work and evaluate them, right? What can we do and what's going to work best in these situations? Make decisions, implement a plan, and then evaluate or iterate, right? What worked, what didn't. Now let's do that more. The things that didn't work, let's not do those as much. And the things that worked, let's do those more. So a basic question that I will ask you right now is, where are we at? If we're asking about soil health related to management and agriculture, let's just talk about California. Now we don't have to talk about big scale. Annual production, perennial systems in California, where are we at? Right? Or do we know that there's a problem? Yes. Have we determined objectives and goals? Kind of, right? We want to do that. We're really kind of at probably somewhere in here, right? We're still at we need to make sure we inventory, analyze, provide alternatives, and try those out, right? We still really are in a kind of incipient phase of this. And part of that we'll talk about later is just California's got such diversity of soils and management systems that it makes it challenging. Other systems, it's more implemented already. They're doing a lot of cover cropping in the Midwest, corn, soybean, rotation crops with cover crops, but that's also still dependent on herbicides to terminate. We'll get into cover crops again soon. But we still really are at this formative stage where we're kind of data limited. We need to know more. We still don't have that much information, and we don't have all the answers with what even to measure. We're going to get to that here in just a second. So here's another way to think of it, and this gets us kind of to the goal, this measurement goal. Soil quality refers to dynamic soil properties that are affected by management or disturbance and/or. Our goal is to assess existing management and develop systems that promote health and function. So how can we take systems that we know we're going to manage? Nut crops are likely going to stay nut crops at the university farm or in the area, and how can we make our management systems better to promote health and more positive ecosystem function, or positive ecosystem services, as we've been talking about. So what do we need? Number one, we need things that allow us to understand what's happening, and in this case, we'll call those indicators right here. Indicators are just measurements that kind of need the following properties. They need to be easy to measure, right? We can measure anything almost now. We have amazing science and tools, but it's not always practical, especially if we're talking about something that needs to be measured multiple times in a field over X number of fields, and it's got to be easy. It's got to be able to assess change. Does it make something get more or less, better or worse? And we also have to be able to decide what better or worse is. It has to be assessed at a reasonable time scale. It has to be able to make measurements over a time scale that matters, and that's not always easy. It has to be accessible to users and applicable to field conditions. The best measurements we can make are easily done by farmers or modestly trained technicians that can be applied at field conditions and at field scales. Hopefully scaled by remote sensing. We'll get to that later. Sensitive to variation in both climate and management. Right? They need to be able to be robust to changing conditions. They need to represent these three categories: physical, chemical, and biological. Those are going to be the three we're going to talk about throughout the rest of the semester. Physical conditions of the soil, the chemical conditions, and biological conditions. And they need to be able to blend qualitative and quantitative. It doesn't have to all be hard quantitative, and often all qualitative doesn't work as well. It's going to be some combination of those. So these are what define indicators, and we need good indicators to assess soil quality or soil health. So the take home right now is that we really don't know all the things that we need to know. We don't have the perfect measurement approach. We don't have agreed upon metrics. We have a starting point, and that's what I'm going to share with you right now. So NRCS has provided an array of soil quality indicators from their national lab and through a variety of different field offices. This is kind of the working set of measurements that people say, hey, let's start here. We know these matter. Let's talk about them. So I'm going to cover physical, chemical, and biological ones right now. So infiltration, right? Infiltration is the downward movement of water into soil. If water doesn't go into soil, you have problems. Now, infiltration is a great measurement that a lot of people want to know about, but it's not that easy and not that reproducible. We'll get to that more later. Soil crusts are an indicator. If you have soil crusts, you have a problem. Here you can see these young seeds trying to pop out of a crust. Crusts form for a variety of reasons. Once again, we'll get to that a little bit more in detail later. Soil structure and macropores. Porosity, as I've already said, is a critical aspect of soil health because porosity allows for water flow, gas transport, water holding, right? More pores allow water to have residence time in soil so plants can uptake it. Aggregate stability, right? The ability for aggregates to resist forces and maintain their structure. Aggregates are what allow for pores to stay in soil. They're what allows for soil to be held together and not to flow away or blow away with erosion. Slaking. Slaking is a measurement of the ability of an aggregate to withstand internal pressures. Now, this is where you add water rapidly to an aggregate, and if it disaggregates or dissolves or breaks down, that means that the physical pressures inside that aggregate are greater than the aggregate can hold itself together. Now, this is important because what happens in agriculture? We irrigate. So if you irrigate a soil and it can't withstand just adding water because it starts to break down, that's an indicator that quality is not assessed. Water holding capacity and bulk density. Bulk density literally is the mass of soil per unit volume. And we'll get to that a little bit more when we start calculating water budget or carbon budgets. But bulk density is a great example of a measurement that's easy to do, that provides you information about porosity, about compaction, and some other things. So those would be your physical indicators that we're currently thinking about. Chemical indicators, there's just a handful. Reactive carbon, I'll be talking about POC, peroxidase oxidizable carbon. It's an index of stability versus oxidation, and it's still not worked out as a perfect example, but it's an effort to try to understand if there's enough carbon there to allow for microbes to do their work and to make nutrients available. Electrical conductivity, right? If you start to have adverse problems with soil management, you can start to build up salts. High electrical conductivity soils often mean that there are soluble salts that might provide problems to both plants and soil health. Nitrate availability and pH. pH is the master variable. Many nutrients are, their availability varies with pH. Also, the effectiveness of soil enzymes and other biochemical macromolecules can be adversely affected by changes in pH. And we know that we change pH through the addition of fertilizers and through some other management practices. So there's 4 chemical indicators that we could think about. Last is the biological indicators. And these are both the most difficult in many cases to measure and the most critical, right? Biological systems, the function of soil related to biology, is really where we need to take most of this, because those other 2, the chemical and the physical, seem to come along with active, healthy biological activity in the soil. So, number 1, total carbon. We need carbon storage, right? With carbon comes nitrogen. With carbon is energy that feeds the system. Organic matter holds aggregates together, provides color, water holding. It's really an important component, and like I said, we'll cover that in greater detail. Particulate organic matter. That means that there's small pieces of not fully decomposed material in the system that allows the system to have energy to move forward, but it's not always that easy to measure. So enzyme activity. We've made great advances in that, but still it's something that's a biological assay that takes some skill and some ability to make measurements. Earthworms. If earthworms are present, that's a good thing. But how do we measure them, right? Soil respiration. As we will find out, the largest flux of carbon in and out of the terrestrial, in the global carbon budget annually is through the drawdown of carbon through photosynthesis, the fixing of CO2 into simple sugars through photosynthesis, and the re-respiration of that carbon back to the atmosphere as CO2 from the metabolic activity of autotrophs plus the decomposition of organic matter. So soil respiration is an important indicator, but how is it easily measured? Now, finally, potentially mineralizable nitrogen. Once again, kind of like the oxidizable carbon or the labile carbon, it's an index of how much nitrogen might be made available. Remember, nitrogen is the most important, in air quotes, or the in greatest demand nutrient that plants need to grow, but it's also in limiting supply. So if you don't have potentially mineralizable nitrogen, you likely are going to have nitrogen deficiencies. So I just covered physical, chemical, and biological indicators. And remember, indicators should be easy, should be pertinent, should be applicable, all those things that we talked about a moment ago. So now you're going to go into your breakout rooms and you're going to talk about fact sheets. There's a bunch of fact sheets available, and I'm going to let you figure it out from here. So hopefully that was useful, and hopefully it set the stage for our conversations throughout the rest of the semester, both in lecture, in our lecture videos, and in our activity sessions moving forward. Thanks. Have a great day.